everyone, welcome to lecture 3 on DC machines, and in this lecture I am going to talk about different types of DC machines and also another topic called EMF equation of DC machines. So let's get started. So the DC machines broadly in the form of connections can be classified as self-excited and separately excited DC machines. So let me begin by telling how these names have come. So one is separately excited and this one is self-excited. So how these names have come is excitation will be that of a magnetic field. So in DC machines, there are two windings. So in DC machines, mainly, so we have field winding and then we have armature winding. Now, as you know, the field winding is used for generating the constant magnetic field, and the armature winding is used for actually generating the voltage and carrying the main load current. So, under field winding, you may have only a series field winding or shunt field winding. So, sometimes only shunt winding you find, sometimes only series winding you find, sometimes you find the both shunt and series windings. So either one winding or two windings you can find in a DC machine. So now the question is how these windings are excited. How these field windings are excited. So when I mean excited, so basically the meaning is DC supply. How these field windings are getting a DC supply. Sometimes there is a separately DC supply is provided. So then we call it as separately excited. And some other times the DC supply is provided by the armature. So then it is self-excited. So this is the terminology. The question is you look at the field winding, whether field winding is getting a separate supply or whether field winding is getting the supply from the armature. So of course you look at the series winding. By definition, the series winding is connected in series with the armature. So therefore, if you have a series winding, then it will eventually go to the self-excited category. But then if you have only shunt winding, then it can be any of these two. So that is what I'm going to draw above. So separately excited, how does it look like? So the separately excited looks like this. So there is a magnetic field, DC voltage supply. There could be a variable resistance here. So this is the field winding denoted as F and FF. So F is the starting part of the field winding and FF is the ending part of the field winding. And then there is an armature winding denoted by this circle and brushes. So this is a generator and then this load is connected here. So this is separately excited. So the voltage of the field can be different than the voltage of the load. So as you say, when I say load, it is the electrical load because generator will have output of electrical. Now coming to self-excited. Under self-excited, there are again three categories. So one is shunt, other is series, and the last one is compound. So let's discuss this. So in the shunt winding, it is like this. Shunt winding is connected directly across the armature winding, and here there is a load. So whenever the armature is generating a voltage, that voltage is applied to the field. So therefore the field, there will be a current and the field will work normally. So but then you can ask a question, what if at the beginning the voltage output of generator is 0? If there is no voltage, then there is no field current and then there is no field, Therefore, without the field, how the voltage is coming into picture. So it's like a situation like this. But then there will be always some residual magnetism in the poles. Because of that, even if the current is zero here, even if there's no field current, some small magnetic field will be there, which will generate the small voltage here, which will in turn start sending more current, and they kind of build up the voltage, and finally full voltage will be achieved here. So that is the shunt generator. In series generator, same thing. The functionality is same, but just the connection is different. The series winding is connected in series with the armature winding. So this is a generator. This is A, and this is F and FF. And here the load is connected. So in compound, there are again two subdivisions. So one is long shunt and another is short shunt. So in long shunt, the shunt winding is there and also both series winding is there, and the connection is like this. Whereas in short shunt, the shunt winding first connected across the armature, then this entire thing is connected across the series winding, and then there is a load here. So these are roughly the different types. So what you are seeing here is something like 1, 2, 3, 4, and 5 different ways to connect a DC machine, and it is called separately excited or self-excited. Under self-excited, again, shunt generator, series generator, long shunt or short shunt compound generator. So based on this, we'll just quickly solve some example problems so you will be able to understand better. Okay, so let's begin by solving an example problem. So look at it. You can attempt it on your own by pausing the video, and now I'll be attempting to solve this problem. So what we have here is a DC shunt generator delivers 400 amperes at 250 volts. So first, it helps in making the circuit diagram. So this is the shunt field winding, and I'll just use a resistance symbol. So this is actually the resistance of the armature. So just actually physically this is inside the armature winding, but just for ease of representation in a circuit diagram, I have just drawn it outside. And even though an inductor symbol is drawn here, for all purposes in a DC machine, because we are studying the steady state condition of DC machine, this is actually a resistor. So if it is a AC, then the inductance will come into picture. So anyway, so let's look at what is given in the question. So this is the load, and what is the load doing? A DC shunt generator delivers 400 amperes. So the load current is 400 amperes. So let's denote it as IL, and at 250 volts. So the terminal voltage here is 250 volts. So does it mean that the armature also generates 250 volts? So actually not. So this is EG. So EG is the EMF generated in armature. It will be slightly more because there will be a voltage drop here. And the resistance is here, it is 0.04 ohm, and this resistance is 50 ohms. So now we have everything ready. So first I can find the field current. So what is the field current IF? So this terminal voltage 250 volts is exactly what is appearing across the field winding. So therefore voltage by resistance RSH. RSH is a symbol for shunt field resistance, and VF is the voltage of the field. So this is 250 volts divided by 50 ohms. So this comes to 5 amperes. So this 5 amperes current, let me mark it here, is flowing in the shunt field winding. Therefore, what is the current in the armature? So armature current, just by applying Kirchhoff's current law, so load current is going towards right side 400 amperes, and 5 amperes is going towards left side. Both of them are supplied by armature current IA. So IA is IF plus IL. So which is nothing but 5 plus 400. So we get 405 amperes. Now we have 405 IA current. I can find out the drop. So armature drop. So this is nothing but IA RA, where RA is the symbol for resistance of the armature. So 405 multiplied by 0.04. So how much does that come to? So let me use a calculator. So 405 multiplied by 0.04. So I'm getting 16.2 volts. So let me write that here, 16.2 volts. So this 16.2 volts will get added to the EMF generated. This is nothing but IARA. Again, this is simple Kirchhoff's voltage law plus V. So V is the output terminal voltage. So therefore I get 16.2 plus 250. So I get 266.2 volts. So this is the voltage generated by the generator. So this completes the first example. So let's look at one more example like this. So this is the question. So a long shunt compound generator delivers a load. So again, when the moment you see a long shunt compound generator, let's begin by drawing the circuit diagram of that particular generator. So long shunt. So that means the shunt winding is long, and there is a series winding here. Then there is a small armature resistance, and then HL armature. I'm just representing like this. And then there is a load connected here. So this is the output voltage. So, and then there is a load. Let's write down the values. So a long shunt compound generator delivers a load of 40 amperes. So this load is 40 amperes load current, and 400 volts. So here the voltage is 400 volts plus minus. The armature series and shunt winding resistances. So armature resistance is 0.04 ohms. Series resistance is 0.02 ohms. Typically, the armature and series resistances are much lesser than the shunt field winding resistance, because the current, that full current is carried in the armature winding. So therefore, the resistances should be preferably less. And also the series winding will be smaller than the resistance of the armature itself, because the number of turns will be less in the series winding. This is just only a typical observation. And 200 ohms is the resistance of the shunt field winding. Okay, calculate the EMF generator and the armature current. Allow the brush contact drop of 1 voltage per brush. So here you see, I'm just symbolically showing brushes here. So there is a 1 voltage drop here and 1 voltage drop here. So typically main two brushes, the voltages drop is like that. So now the question is, find out what is the generated voltage EG and what is the armature current IA. So again, to find armature current, first I find the field current. So field current will be field voltage divided by field resistance. So what is the field voltage? 400 volts divided by field resistance is 200. So we get simple 2 amperes. So this current going this way is 2 amperes. So therefore 40 amperes is going on the right, 2 is going on the left. So that simply gives IA to be 42 amperes. So IA is nothing but IF plus IL. This is 42 amperes. Then drop in the series and drop in the armature. So drop in series and armature windings. So it's nothing but IA current multiplied by R. I can calculate them individually, RSC plus RA, or I can just add them and then finally calculate that. So I get 42 multiplied by 0.02 plus 0.04. So that is nothing but 42 multiplied by 0.06, which is nothing but 42 multiplied by 0.06, 2.52 volts. Now this voltage will be added to the total voltage to get the, of course I'll have to, also have to add the brush drop. So total voltage drop is 2.52 plus brush voltage drop. So that is nothing but 4.52 volts. So therefore, voltage generated Eg is nothing but voltage drop plus output voltage V. So that is 404.52 volts. So this is what was asked in the question. What is the generated EMF and what is the armature current? So both we have calculated in this. So let's look at more examples. Now let's look at this problem. This is third example. So a short shunt compound generator delivers a current. So again, it will be nice to begin the solution by making a diagram. So you can always pause the video and you can attempt take 5 minutes time and attempt the problem, and then you can compare your results with the results which I get. Okay, so let me attempt this problem now. Short shunt compound generator. So let me draw the circuit diagram of a short shunt compound generator. So this is a shunt field winding, and there will be armature resistance and the armature itself, and there will be a series field winding, and then there is a load here. Current of 40 amperes at 240 volts. So the load current is 40 amperes. And the load voltage is 240 volts. The resistance is, the armature resistance is 0.05 and this is 0.04 and this is 200 ohms. And there is a 1 voltage per drop. So here it is 1 volt, here it is 1 volt. So I am writing this so that I won't forget. And then I'll have to find what is the IA armature current and then what is the EMF generated EG. So again, ultimately, if you look at it, solving this kind of problems, nothing but, it's a DC networks, just very basic DC network solutions only. So obviously by looking at this, in order to find armature current IA, I need what is the field current IF. And I also need this load current is given. So, but in order to find the field current, I need to know what is the field voltage. So for that, first I should know the voltage drop here. So V drop in series, or let me call it as VSC, is nothing but I load multiplied by RSC. So the load current is 40 amperes and the series resistance is 0.04. So this to me looks like 1.6 volts. So 4% of 40. So now this voltage will be added to the total voltage to get the voltage of this point. So because some voltage is dropped here and the remaining voltage is 240. So therefore VSH shunt field voltage will be nothing but total voltage plus voltage of series field winding. So this is a kind of a relation that comes because of the short shunt connection. So I have 240 volts here and I have 1.6 volts here. So therefore this is 241.6 volts. And given this voltage, now I can find out the field current. So that is nothing but ISH or IF, which is nothing but 241.6 divided by 200. So how much does it come to? Let me open my calculator. So 241.6 divided by 200. So I'm getting 1.208. So I'll approximate to, or I'll just keep it accurate, 1.208 amperes. So this much current is coming in the field winding. So therefore, what will be the armature current? So armature current will be field current plus load current, as you can see in this. So that is 40 plus 1.208. So this is 41.208 amperes. So now that I have the armature current, so now I can find out the armature drop, IARA. So that is 41.208 multiplied by 0.05, which will be, so I'll just add 41 to it. Oh, I'm sorry, 41.208 multiplied by 0.05, 3.268. So therefore, from all these things, I can find out the generated EMF. That will be 2 volts for the brush contact drop, plus the voltage drop in the armature winding, that is 3.268 volts, plus I already know the voltage of this point, which I already calculated earlier, 241.6. This is again just a simple application of Kirchhoff's voltage law. So let me do this addition. So this already I have. So plus 2 plus 241.6. 246.868. So I'll just round it off to 246.87. So I have calculated EG and I have calculated IA. So let's check what else is asked in the question. So okay, as far as question is concerned, just these two are sufficient. Now let's look at one more problem. So again, there is a question given in front of you. So here some new thing is there, that is series field diverter. So this is the resistance which is connected in parallel with series winding. So this will slightly reduce the current in the series field winding. So apart from that, rest of the question is same. Again, you can pause this video, you can try to solve this question yourself and check your answers with my answers. So meanwhile, let me begin my answer. So as usual, I'll begin by drawing the circuit diagram. So what is this? This is a long shunt compound DC generator. So let me use this place. I'll draw it here. This is the long shunt generator. This is the load here. So 230 volts. So 230 volts is the output voltage. So the same 230 volts will apply to the field winding, and you see shunt field resistance is 100 ohms. So therefore from this I can calculate 230 volts divided by 100 ohms. So I'll get 2.3 amperes flowing in the field current. So one thing we already calculated. The series resistance is 0.015 ohm. Series field diverter resistance. So let me draw the diverter also. So this is a diverter. So what this diverter does is some of the armature current gets diverted to this, so that will slightly weaken the series field. So the applications of this maybe we'll discuss later in this course, but right now just as per the data given we'll solve it. So this is 0.03 ohms. This is the resistance of the diverter, and armature resistance is 0.03 ohms. Determine the following armature current. So I think the load information is not given. So since it is a rated is 35 kV, so assume full load operation. So if the generator is delivering full load, that means the output is 35 kilowatt. The input may be more than 35 kilowatt, but the output is that. So load current will be nothing but power output, that is 35,000 divided by 230 volts. So how much is this? 35,000 divided by 230. So I'm getting 152.17. Okay, so let me make a note of it. 152.17 amperes. So this current is flowing here. So therefore, the current that will be flowing in the armature, I can just, so which is here and here, I can just add these two. So armature current will be 152.17 plus 2.3. So that will be plus 2.3, 154.5. So I'm just rounding off this 0.47. So this will be 154, or I'll just keep it 47 amperes. So armature current I have calculated. Now, how does this current split between these two? So what is the current in the series field winding and what is the current in the shunt field winding? So just simple current division rule. So when the total current is this one, 154.47, and if I multiply with, like example, I want to find the series current, then you take the opposite resistance, 0.03, and then divide by the total resistance, addition of these two, 0.03 plus 0.15. This will give me current in the series field winding. So how much is that? So this I'll multiply with 0.03 and then I'll divide with 0.03 plus 0.15. So this will give me 25.74 amperes. So therefore the remaining current, so here the current is 25.74. So out of total 154.47, 25.74 is going this way. So the remaining I diverter current, ID, will be nothing but 154.47 minus 25.74, which will be, so I'll just minus 154.47. 128.7 volts. So 128.7, sorry, amperes. So this turns out to be the diverter current. Oh, I think I made a mistake. So this is 0.015. So let me just go back and correct everything. So 154.47 multiplied by 0.03 divided by 0.03 plus 0.015. Oh, so this is 102.98. So that's what I will, how did I come up is, because this resistance is less than this resistance, so more current should be flowing in this path. So when I compare these two, it was not coming correctly. So let me just correct it myself. So this is 103 amperes. So 102.98, I just round off to 103 amperes. So this will be nothing but minus 103. So that will be, so 51.47 amperes. So I got the diverter current also. So now the thing that is left to be calculated is the EMF. So armature current, I think I have already calculated. EMF induced in the armature, I have to find the EMF induced in the armature. How do I find it? So EMF induced in the armature, EG, is nothing but total voltage plus drop here plus drop here. So let me do that. So EG is nothing but terminal voltage plus IA RA plus ISC RSC. So this term is, anyway, since it is parallel, it is also equal to ID into RD. So anyway, let's do that now. So output voltage is 230 volts. Armature current is 152 point, that is 154.47. this multiplied by armature resistance, which is 0.03 plus ISC RSC. So series current is 103 amperes and series resistance is 0.15 ohms. So what is this? So again 230 plus 154.47. Let me do it from the beginning. So 230 plus, I open the brackets, I think 154.47 multiplied by 0.03 and close the brackets, plus again open the bracket, 103 multiplied by 0.015. So hopefully this is all correct. 236.179 or 236.18 volts. So this is the EMF generated. Brush voltage drop is not given, so I am not considering that. Alright, now power consumed by each component. So this is again interesting to make you understand the concept better. So what we have to do now is the component and power consumed calculation. So first let's look at the load. So load already we know that is nothing but voltage of load into current of load, that is 35 kilowatts. So this already it is known. Next, what is the power consumed by the shunt field winding? So this is nothing but ISH square RSH. So what is the shunt current? Here I can see in the drawing 2.3 amperes. So I'll just do 2.3 multiplied by 2.3 multiplied by 100. So this will give me 529 watts that you can see on the screen. So that I'll write here. And what is the series field wind drop? Power consumption in the series field. So ISC square into RSC. So which is nothing but 103 square into series resistance is how much? 0.015. So this comes out to be 103 to the power of 2 multiplied by 0.015. So it is 159 watts that is being lost in the series winding. Diverter. So is nothing but ID square RD. So what is the diverter current? So I can see here 51.47 amperes. 51.47 square multiplied by 0.03 is the resistance, I remember of that. So what is that? So 51.47 multiplied by 51.47 multiplied by 0.03. That is 79.47. So I'll just write 79 watts. I'm just rounding off to the nearest watt. And armature resistance also. Because of the armature resistance, so this is IA square RA. That is nothing but, what is the armature current? 154.47 square. 154.47 square multiplied by RA 0.03. So how much is that? So 157. I'm sorry, is it? Oh, it is 154. 154.47 square multiplied by 0.03. So 715.8. So or I'll round it off to 716 watts. So these are all the components where the power is being consumed. So if I add this, so let's add this. So 35,000 plus 529 plus 159 plus 79 plus 716. So it is 36,483. So this is the total power. Now, what is the source of all this power? The source of all this power is nothing but this EMF generated that is here. So therefore, if I multiply Eg into Ia, that is the total power, total electrical power developed. So electrical power developed will be EG Out of that, if I remove all these losses, so this loss, this loss, this loss, all these things, if I remove it, then whatever finally goes to the output is the 35,000 watts. So let's verify whether our answer is correct. If I do this, I should get this quantity back. So what is EG? 236.18 volts. So 236.18 volts and multiplied by IA. IA is 154.47. If I did this correctly, then this value should be almost matching with this value. So let's verify that now. So 236.18 multiplied by 154.47. So I'm getting 36,482.72. So this is almost equal to this. So we are getting validation. So ultimately what is happening is, if you look at this diagram, the electrical power is being generated here, and for all the internal copper losses, some copper loss is gone, and finally output is going to the machine, that is the total output, that is electrical output, that is 35 kilowatt. I hope from this problem also you understood something. So let's continue our study. Now let's come to a new topic, that is EMF equation of a DC generator. So far we had looked at the external connection of the DC generator, that is outside, whether it is connected in shunt configuration or series or long shunt or short shunt, like that. But now looking at the internals of the machine, I want to know what is the EMF equation. That is, look at the machine. So if you can simply recollect, you have like the machine construction. So this is the yoke of the machine, and there is a pole shoe here, and there is another pole shoe here. Forgive my clumsy drawing, but then this is the winding, field winding, and field windings are what is responsible for generating a field. So F and FF. So let's say this is the north pole and this is the south pole. A magnetic field is set up, and in between there is a armature. Armature having a lot of slots, and one of the slots, if you consider one conductor, so this conductor is rotating in this particular magnetic field, and then it will once it rotates the magnetic field, it will induce EMF in that particular conductor. So let's with this brief overview of what is the working principle of DC generator, let's write down some expressions. So let's define phi is the flux per pole. So in Webers. So this particular has phi amount of flux, and this also has phi. So total flux here is 2 phi actually. So that way you need to count that flux per pole. Now, so this is in the flux per pole is actually constant. Unlike in a in an AC machine where the flux keeps on varying, here the flux is constant actually. So it's like a constant DC value. So now P is the number of poles. So for this diagram, P equal to 2. But then there could be 4 pole machine, 6 pole machine, 8 pole machine, 12 pole machine, 20 pole machine, whatever. So the number of poles can be any even number, as far as the construction of the machine allows you to construct. Now let's denote quantity Z or Z, which is number of conductors. So I had shown only one conductor here, but like this there will be a number of conductors spread across this particular armature. And with this information, let me also add one more, that is N is speed of armature in revolutions per minute. So the armature is being rotated by a prime mover at some speed. In 1 minute, how many revolutions it is making. So that is the speed here. So given this information, so let me write down. So there's also another thing, that is number of parallel paths. That is denoted by A. So basically, as a part of this subject, the types of windings, we are not going in depth. So there are mainly two types of windings. One is lap winding, and the other is wave winding. I'm not going into in depth how these exactly winding diagrams are made. You can refer to any good textbook, you will be able to find this. For the purpose of this course, I'm just giving you a brief overview. In lap winding, what happens is, let's say these are all conductors. So all conductors are allocated equally to each pole. So therefore, we'll get Z divided by P parallel paths. So if there are 100 conductors and 2 poles, so there will be 50 parallel paths. I'm sorry, this is not the correct one. So the number of parallel paths will be actually equal to the number of poles. So if there are 100 conductors and 50 poles, so 2 poles, 50 will be connected in series. So half will be connected in series, remaining half will be connected in series, and this will be one path and this will be other path, something like that. So basically it's an allocation of armature conductors into different series parallel combinations. So in the lap winding, A equal to P, and in the wave winding, A equal to 2. In the wave winding, only 2 parallel paths are made. Now this you will have to kind of remember it, otherwise you will have to go into details of it. So how to remember it is, you look at the word LAP, lap winding. So you see A and P are there, so you can just remember A equal to P, that is parallel paths equal to number of poles. Similarly, when you look at the word wave winding, so the wave has 2 dots below here, so that, or 2 sharp edges at the top of the wave, so that will tell you A equal to 2. So something like that. Okay, so let's go back to deriving the EMF equation. So what you do is this: look at this conductor. This conductor is making 1 revolution. Under 1 revolution, how much flux it will cut? So EMF induced, as you know, Newton, that is Faraday's law, d phi by dt. So rate of change of flux linkages. So what is d phi? So that is nothing but p phi in 1 revolution. So flux per pole multiplied by number of poles will be the total flux being cut by one conductor. Alright, what is dt? So now you see n revolutions per minute is the, so this is dt is time for 1 revolution. Now how do we derive that? You see, n is the speed of the rotor for revolutions per minute. So if I make it 60, this is revolutions per second, and if I take the inverse of that, this will be seconds per revolution. So that's nothing but time for 1 revolution. This is dt, or this is nothing but 60 by n. So now I'll say EMF induced in one conductor is equal to, so that is nothing but d phi by dt, so that is p phi divided by 60 by n, or nothing but Pn phi by 60. This is EMF in one conductor. Now what about EMF in one parallel path, which is nothing but total EMF. So EMF in parallel path is nothing but EMF per conductor multiplied by number of parallel paths. So conductors per parallel path. So there is a Z and then A will be your answer. So finally I'll get a Pn phi Z by 60A. So this is the EMF equation for the generator. So based on this, let's work out. So A equal to 2 for wave winding and A equal to P for lap winding. So this also you can just add as a additional information. Let's work out some problems on this. So based on the previous explanation, let's try to solve this problem. So the data given a 4-pole DC generator. So therefore what I know is P equal to 4, having wave wound armature winding. So if it is a wave winding, that means number of parallel paths A is nothing but 2. How do you remember? Because wave winding has 2 sharp edges at the top, not counting this one. So that is 2. Anyway, so let's continue. Wave wound armature winding has 51 slots and 20 conductors per slot. So total conductors is nothing but slots multiplied by slots per conductor. Sorry, conductors per slot. So total we have 51 slots and multiplied by 20 conductors per slot. So this comes to 1020 conductors. Flux per pole is 8 milliwebers. So 0.008 webers. So be careful with the units. So given 8 milliwebers, I should write it in webers like this. What is the EMF generator when motor is driven at 600 RPM? So N is 600. So now everything is there. So if I just refer to the EMF equation, Pn phi Z by 60 into A. So EMF is nothing but Pn phi Z divided by 60 into A. Now, one thing, how do you remember this equation? So it is actually quite straightforward. See, what happens if I provide more number of poles? So if I provide more number of poles, there are going to be more flux and more flux linkages. So therefore, E is proportional to P. So a 4-pole machine will generate lesser voltage compared to 8-pole machine, all other things remaining constant. So that is E proportional to P. That is logical, that is understood. Similarly, N is a speed. So if I rotate faster, then more EMF I can generate because d phi by dt. So therefore, E is proportional to N. What about flux? Of course, E is proportional to flux. If I have more flux, more flux linkages it will result in and more EMF can be generated. And similarly, what is this Z by A? So Z by A is conductors per parallel path. So the voltage keeps on adding. So see, the EMF induced is proportional to conductors per parallel path, because if all this voltage is getting added, the number of conductors in series, it will get added. So therefore E is proportional to Z by A. So just by thinking, I can write like this, and this N is only just a conversion. I'm converting the revolutions per minute to revolutions per second. So therefore that 60 factor is coming. So it is pretty straightforward to remember it. So 4 poles, 600 RPM and 8 milliwebers. I can write like this also, 8 milliwebers and 1020 this and 60 into 2. So this is what I need to calculate to get the EMF. So let's use my calculator. So I have in the numerator 4 multiplied by 600 multiplied by 0.008 multiplied by 1020. This entire divided by 60. So again it's divided by 2. So I'm getting 163.2 volts. So this is the EMF generated in the armature. I think that's what is asked in the question. So let's continue and let's do one more problem. So again, you can have a look at this question. You can pause the video. You can try it yourself, and later you can confirm your answer with my answer. So meanwhile, let me begin my answer. So what do you have here? 8 pole machine. So P equal to 8. 500 armature conductors. So Z equal to 500. Flux of 50 milliwebers. So per pole. So that is 0.05 webers per pole. EMF generated is the lap connected running at 1200 RPM. So number of parallel paths equal to number of poles, and then running at 1200 RPM. N equal to 1200 RPM. So because this is lap winding, I'm getting this relation. So it is 8. So up to here I'll solve it. So just easy. Obviously, it should be proportional to P, it should be proportional to Z, it should be proportional to phi, it should be proportional to N, and 60A will be in the denominator. So 8 into 500 into 0.05 into 1200 divided by 60 into A is again 8. So 8 right away gets cancelled, and let me cancel out this also. So 6 2s are 12, so this will be 20. And then these 2 zeros will strike off this decimal point. So I have 5 into 5 into 20. So that is 5 into 5 is 25 multiplied by 20. So this is 500 volts. So the EMF generated now I am getting 500 volts. Let's continue. What must be the speed to generate same EMF if the armature is wave connected? Alright, so if wave connected, then A equal to 2. So therefore, let me substitute. I want to generate the same voltage 500, and the poles are 8, conductors are 500, and flux is 0.05, and speed I don't know. What should be the speed? So, and this is 60, and number of parallel paths is 2. So from this, I can find what is the N required. So right away I can cancel this 500. There will be a factor of 1 here. So therefore N will be 60 into 2 divided by 8 into 0.05. So 2 goes 4 times, and 4 goes 15 times. And then this, I'll remove this and put 2 zeros here, and then 5 goes 300 times. So now if it is a wave connected, then if I simply rotate at 300 RPM, still I can generate more voltage. So there is wave generates more voltage for same speed, because the number of parallel paths are less and series conductors are more. So I hope you learned something from this. So let's continue. Conclusion of this particular lecture 3. So let me briefly review this lecture once again. So first we begin by talking about types of DC machines, where externally how the DC armature is connected with the field and series windings is what classifies the DC machines. I talked about separately excited DC machine, where a separate magnetic field voltage source is given for the flux, and then the generator is connected directly to the load. Whereas under self-excited scheme, the field winding gets the voltage from the armature winding. So that is what is the shunt machine, and this is the series machine. And then the long shunt machine looks like this, and the short shunt machine looks like this. So 1, 2, 3, 4, and 5 different ways of connecting the DC machine. And when I keep the heading DC machine, it covers both DC generators and DC motors. So this is what is the explanation about that. And then we solved one example where the EMF induced has to be calculated. So it is again simple application of your knowledge of your DC circuits. So given the load, you know load current, and given the voltage, you can calculate the field voltage and field current, and field current and load current will add to armature current, and then armature voltage drop, and you can add to the EMF generated. So total this like this. Similarly, we have one more question about long shunt. In long shunt, this is the connection, and again very similar question was asked. So that also we had looked at it. So moving on, we solved some more problems. So I think I have solved 4 examples for this particular way. So we solved one problem on short shunt, one problem on long shunt, one problem on simple shunt, and so on. So this is again a similar problem. And here in this problem, what is interesting is one is the diverter, how the diverter is placed to divert some of the current, and then the concept of electrical power developed, Eg into Ia, and what are the various losses and various outputs we are trying to see in this problem. And finally, coming to the EMF equation. So this is a briefly explanation of how the DC generator works and generates EMF. And I have denoted flux P and Z and N. And then we're not done much discussion about lap winding and wave winding, except remember that in lap winding A equal to P, parallel paths equal to P. And how to remember? Because in the name itself, LAP, it is there. And coming to wave winding, the parallel paths will be 2. And a bit of derivation, EMF induced is nothing but d phi by dt, and rate of change of flux will be P into phi, and time will be 60 by n revolutions per second. And just simply we substitute in this, I'll get EMF induced in one conductor, then EMF induced in one parallel path I can get from this, and this is the total EMF equation. And it is also not very difficult to remember, because EMF generated is, as I have written here, proportional to P, proportional to N, proportional to flux, and proportional to Z by A. So in fact, if let me add a point here. If you look at this equation, so P is constant, and number of conductors is also constant, and number of parallel paths is also constant. 60 is also constant. So if I denote all these things with Ka, see, dynamically I cannot change the number of poles once the machine is constructed. So if I define this as Ka, then Eg is nothing but Ka multiplied by N multiplied by phi. So this is the EMF generated is proportional to the speed and flux. Either you have more flux or you have more speed of rotation to generate the more voltage given a fixed Ka. So from this, I can actually write Eg1 by Eg2 is nothing but N1 phi 1 by N2 phi 2. So again, if some of the parameters are given, one of the other parameter can be calculated based on this. So then we solved a couple of problems on it. So I hope you learned something from this, and we'll be further continuing in lecture 4 later. So for this topic, lecture 3, I conclude here. So if you like this channel, please subscribe to this channel. Please like this video, and so that you can also get access to more videos on this. Thank you.